Welcome. My name is Opubo Benebo. Undoubtedly, the post-harvest context will bring forth large quantities of biotic waste, portions of which have been decided to be used to produce biofuel for the electric power generation, and the remainder used for production of process biofertilizers for the next farming season. This, of course, is rational because the farming operations is not expected to be a one-off operation after all, but rather an ongoing operation, and hence requires continuous improvement, and the post-harvest circumstances is the sort of rinse, repeat circumstance that needs to be fully embraced to evaluate the distribution of the farm waste for raw materials for the biofertilizer supply program, driven on the production with an underlying technology with improvement retrofit designs. As is currently operating, the biofertilizers production equipment is designed to support the production of just compost bioreactors out of farm waste. There is, however, the need to actually produce process biofertilizers for the rapid growth of the crops. The production of the compost biofertilizers was conducted by permitting the two stages of anaerobic digestion reaction, hydrolysis and acidogenesis, and then let open the reactor to introduce the oxygen environment to the reaction mixture and let die the microbes of anaerobic digestion. While the method of composting as used is effective in producing biofertilizers, much of the output compost biofertilizers are not macroparticles, and as such, the absorption of these particles by the plants was not reasonably fast, but was rather delayed. Even so, there was benefit to many subsistence farmers using such composting method. The granularity of the compost fertilizers permitted the design of the soil to be drained for many of the cases of farming that required well-drained soil. Yet, process biofertilizers, which will include in-mixed compost, will not only allow soil drainage, but will also limit frequent watering and also have numerous microparticles that the plants readily assimilate, and that makes the soil always porous enough to force good drainage. So retrofit engineering designs of porous process biofertilizer process that is an improvement on the existing system is a sensible thrust of development. In synopsis then, this episode, entitled Process Biofertilizers for Subsistence Farming, addresses the considerations of on-site production of process biofertilizers for use in the farming process of subsistence farms, elicits the higher productivity advantages for opting for process biofertilizers even over compost biofertilizers, not to mention chemical fertilizers available for garden stores for purchase, and the financial benefits for actually implementing the on-site production of process biofertilizers. The driver rationale for use of process biofertilizers is to ensure that the top surface of the soil forms a film-like structure that prevents excessive evaporation of the water after watering the plant, and thereby minimizes soil drying, and yet always keep the soil moist. The process tasks due to be performed in the production of process biofertilizers includes the primary two reaction stages of anaerobic digestion, extended by the conversion of the post-digestion mixture as a feed for an algae cultivation bioreactor, in which algae feast on the nutrients of the mixture and assimilate the nutrients, and by the metabolism reconstitute the nutrients into forms readily assimilated by plants. So, well-designed biofertilizer process would have the reactions performed in several separate and different bioreactors, and therefore require multiple bioreactor process design. However, the small land space on which the subsistence farming is contextualized requires that the multiple reactor design concept be devolved into a single bioreactor production process. In addition to the land-constrained choice of single multi-process bioreactor use, the version, albeit first on the farm, is indeed the better of the two options, as can be surmised from the features as delineated presently. The single multi-process operating state of the bioreactor ensures that the consequential energy consumption is reduced due to the reduction of the wiring and the associated dissipation losses. As such, the improvement retrofit design will be made on the existing equipment so that the production process is confined to the one equipment. Moreover, the improvement design would enable the additional tasks to be performed. Even so, the operating of a bioreactor, of course, admittedly requires certain specifications. These specifications at a minimum include energy demand load, additional nutrients need for the microorganisms engaging in the metabolic digestion of the biotics in the digester, energy storage needs, or the continuous storage need. The nutrients feed process also requires some improvement retrofit design. Although with this class of anaerobic digesters bioreactors, the second reaction stage products is constituted of all the nutrients need of the microorganisms, both the macronutrients and the micronutrients. The algae nutrients requirement sort of varies slightly, so an additional nutrient feed may still be necessary. In that case, the feed of the biotics is rather straightforward and the microorganism is co-fed with the nutrients, while additional nutrients while being pumped into the bioreactor. Optionally, the nutrients feed point will be kept as close as possible to the inlet port of the bioreactor as to minimize pre-entry reactions that would be forced by the heterogeneous mixedness state of the feed suspension mix. This requirement is made all the more important because of the need to co-feed both the macronutrients and the micronutrients at the same time. So then another much smaller similar equipment is added to the module as nutrients tank, from which the nutrients are pumped into the primary feed stream. The equipment design improvement of the bioreactor is far more complex than the regular batch compost biofertilizer production equipment. That is because provision has to be made for addition of new forms of microorganisms, specifically algae. Nutrients feed port has to be developed, controller system has to be implemented, and the top cap will have a gas flow-through check valve pipe device for the gas outlet, and also have a port for affixing a sterile rod through and holding the impeller at the inside end. The external end is then affixed to a gearbox of a motor that steps down the speed of the motor. So the suspension is being able to steer as the algae nutrient suspension mix flows in and ultimately also out of the equipment. By and large, the bioreactor design in essence is virtually the same as an algae cultivation bioreactors, except for the temperature stabilizing outer jacket. The design construct of typical suspension algae cultivation bioreactor equipment is a tank inside another tank, which simply jackets the inner one, enveloping the trunk of the inner tank with water in it to keep the temperature constant, and has inlet at the bottom and outlet at the top. Although the nutrients are usually microorganism specific, the biotics waste, being generic nutrients, can still be customized with the addition of specific nutrients to form a composite nutrient mix better suited for the organism of choice. Customizing the intrinsic nutrients can be made with selections from options of collected nutrients scoped by improvisation from everyday resource as to be reasonably generic for all microorganisms. The nutrients pool offering the options can be scoped as Epsom salt, seawater or sea salt, tomatoes, citrus fruit plates, pineapple, ginger, and by preference only, vitamins. However, the best approach towards the adoption of the bioreactor system is to start with the batch approach such that the nutrients customization feed tank can be affixed to the top cap but operated in batch mode. The specifics of the design of the reactor can be homogeneous suspension itself, both reaction mixture premixed with the algae. The design and fabrication of the various process equipment adopted throughout the presentation are quite challenging, but can be realized. Again, in a rural setting, a blacksmith would help with the fabrication and assembly. In a more technological society, a mechanic in a machine shop might be engaged for the same help. In rural communities, with the skill set of a blacksmith working on consultation with an engineer or two. On the other hand, in fairly developed societies, the performing of the same task will be undertaken through a machine shop by a machinist also working in consultation with an engineer. Worthy of note is that the choice of the use of suspension homogeneous reactor also brings about an issue that must be contended with. Though the biotic waste may have been fully recovered by the end of the process, a waste mush consisting of the dead fermenting microorganisms would obtain and will have to be disposed of. Yet even this waste can be fully utilized in the farming activities, again by feeding it back at the beginning into the anaerobic digester stage before we go back to the next cycle again. The conclusion that could be drawn here at this time is that a clear, well-defined augmenting retrofit designs for the compost biofertilizer process equipment can be developed and be adopted onto the equipment for the deployment of the improved equipment as to be used for the production of fully-fledged process biofertilizers as can be produced with a true biological process technology. Although a more somewhat scientific and engineering process is suggested for the improvement retrofit designs, the implementation of the retrofit should give the farmer relief from the watering routine as to focus on other issues without having to be frequently returning to check on watering needs and performing watering. Admittedly, some expenses are required initially, often called capital investment, to acquire the composting design, but the availability of the biofertilizers at all times certainly empowers the farmers to conduct subsistence farming all year round. In addition to this circumstance, also ensures lower cost of access to food with the avoidance of purchases of biofertilizers. Moreover, the farmer is now in a position to produce processed biofertilizer all year round, the benefits of which will become obvious in future presentations. Clearly, as of this point, the actions taken so far have enabled the farm to farm with one biofertilizers grade for all the crops, irrespective of the soil requirements, as may be observed by other farmers. And it is a wrap. On that note, I say to you, thank you so much for having come to listen to this observation about efforts aimed at alleviating world hunger through subsistence farming by both urban dwellers and emerging countries' small farm farmers. You are truly appreciated. If you would like to get privileged viewer reader information, or access podcasts of specialized concepts, or access even vertically integrated concepts, then I implore you to join my support club and enjoy that privileged status. Meanwhile, while still here, do please take a moment and subscribe to the channel as to be informed of the publication of every new episode as soon as it is released. Thank you. Bye. Till next episode.